Hi everyone, this is Carolyn, and in this video we're going to talk about how to calculate the mean of a discrete probability distribution. Again, we are going to remind ourselves through this video also what a discrete probability distribution is. So I want you to first of all remember from my last video, and if you didn't see the last video, that is okay, but we had a basketball player who's going to be shooting 3 free throws. And what we're going to do is let X be the number of shots that they make. So X has the following discrete probability distribution. Discrete meaning that X takes on finite values. So 0, 1, 2, and 3. It does not take on a continuous spectrum of values, which would be a continuous probability distribution. Probability distribution simply means that we have a listing or a way to find all of those probabilities associated with all of the possible outcomes for our random variable. Since we're shooting 3 free throws, we could have make none of them, 1, 2, or 3 of those. And P of X is just randomly chosen or given based on this particular basketball player's ability. And what we want to do is we want to find the average. So how do we find the average or our mean? Reminding ourselves what the mean symbol we used is mu. We want to know how in the world would I find the average number that they would shoot it. So thinking of this basketball player getting up to the line, shooting 3 free throws over and over and over again, and someone recording how many they make. Sometimes they're going to make none of them. Sometimes they'll make 2, sometimes they'll make 1, and so on and so forth. Based on these probabilities, which we can also kind of think of as percentages, for example, 10% of the time, roughly speaking, this person's going to make 1 out of his 3. So the person will write down the number 1. 38% of the time, they'd make 2 of them. At the end of however many times we wanted to do this, we'd add them all up and divide by the total number that we had. But we can also do this as a weighted average, where the weights are those probabilities that we have, because we would have 10% of our scores or numbers would be the number 1. So we can take that value times its weight, or how often it occurred, or like 1 out of every 100 we'd have a 0. We would have the number 1 about 10%, or 10 out of 100. So if you wanted to do it thinking of it as 100 times, we would be then adding the 2, 38%, or 38 out of the 100, plus the 3, 51 times out of that 100. So then multiplying it by the 51, adding them all up, dividing by 100, or I can use those weights. And if I do this, we would get the number 2.39. So on average, every time he gets up to shoot, he makes between 2 to 3 of those shots. So on average, 2.39 of those shots. Okay, to put this into a formula, if you are looking for the mean of a discrete probability distribution, I'm going to abbreviate distribution there, just DIST. So to calculate our mean, what did we do? Well, we added up. So I'm going to use that addition symbol, our summation notation. So sigma. We took our X values as they went through all of the X's, but we also multiplied it by our P of X, and then we added all those pieces together. So you can think of this as a weighted average, so to speak, weighted average. Sometimes we don't always call this the mean. Sometimes we will refer to this, sometimes, the mean is referred to, in this instance, as the expected value. Because we expect over time to have them make 2.39 out of those 3 shots. So we expect, it's kind of like what we expect them to do. Let's do another example, so you can kind of see where else this kind of shows up. I have 2 more examples that I'll walk through. So the first one, let's just play a game. So, or gamble if you want to, but we're going to call it playing a game. This game will cost us $4 to play. Okay. And what this game is, what we're going to do is we're going to roll our die, roll a die, and we'll call it a regular 6-sided die. Okay. You might say you're going to roll 2 die, and if you get a 7 or 11, you get all these different pieces. So we could make this more complicated. I'm just going to make this kind of a simpler game. And what happens is you or we, whoever you want to word this, you will receive the number of dollars as shown on the die. Okay. So in other words, if we roll a 5, we will receive $5 back. So, and what our question is going to be is, in the long run, so if we did this over and over and over and over and over again, what can we expect? What can we expect to win or lose on average per game? Okay, so what we're going to have to do is figure out what's going on. So I'm going to write this as a probability distribution and use that idea to figure this out. So here's what I'm going to do. I'm going to do it in a couple of different steps. So what could happen? So we roll this die, right? And well, either the die is going to be a 1, a 2, a 3, a 4, a 5, or a 6. Now, that's not the value or the outcome to us as far as this game goes. So I'm going to put that value in here. So the value of rolling that 1 is actually, well, we paid $4 to play. We roll the 1, we get $1 back. That means we are in the hole $3. If I roll a 2, I'm in the hole $2. Rolling a 3, I'm at a -1. If I roll a 4, I break even, so to speak. So my value of that roll is nothing. And I have a 1 here and a 2 here. We also need our probabilities of each of those things happening. If this is a fair die, all of those probabilities are 1/6. Whoops. So I'm going to put that in there. And so our expected value, what we expect to achieve or win or lose, or we can think of this as the average, our mean, mu, we're going to take that -3 times a 6, add that to a -2 times a 6, add that to a -1 times a 6, add that to 0 times a 6, Add that to 1 times a sixth. One more, 2 times a sixth. And if we do all this math, getting out our calculators or knowing that this is going to be 0, this is going to be a negative of this one, so these cancel out, those cancel out. I'm left with that negative 3 over 6, which is a negative 0.5. We can expect to lose roughly 50 cents per game. So every time we roll our die, in the long run, we would lose on average 50 cents per game. So if we played 15 games, we would expect to be down $7.50. If we played this 15 times, we could expect to be out that 15 times the negative 0.5, which is going to be that negative 750. So we'd be down about $7.50. Okay, so there's an example of kind of like this idea of expected value in a gambling or odds type of situation where there's a payout. Okay. It doesn't always have to be payouts, but this is something that is used a lot too in life insurance policies. And again, for this example, we're going to simplify the situation a little bit. And we're going to have that Tommy. And he pays, well, let's say $240 per year for a $250,000 policy. Okay, which means that if something were to happen, the life insurance policy would be able to get cashed in, and Tommy would get, or not Tommy because he's gone, but his family survivors would get that $250,000. Okay, and let's just say, based on statistics for Tommy, his age and physical situation, and they can do this, they track all this data, and they can kind of determine based on your age and a whole bunch of other different things that the probability you're going to live for a year or die. So let's just say that the probability that Tommy passes is 1 out of a very, very large number. So there we go. So it's not very likely that he's going to pass. Okay. We want to know, what is the value of this policy from the viewpoint of the insurance company. For that 1 year, for this particular year. Now, every year it's going to change because the probability of Tommy living or not living changes as we age. The chances we're going to live another year go down a little bit. It just happens. So what we're going to do again, this time we're going to look at it from the point of the insurance company. So they're the ones paying out the money. In our previous example, we looked at it from the player, not the person who is performing the game, such as like a casino. So we're going to kind of turn the tables a little bit and look at it. And again, what could happen in this situation? Well, Tommy could live, which would be great, or he could not live. So I'm just going to put he's going to live or die. Okay. Now we want to kind of know from the aspect of the insurance company. What is the value? So what is that value, which we'll call X, of him living? Well, if he lives, they get to keep that $240 piece and nothing's paid out. So they're making that $240 for that year. If he passes, they have to pay out this $250,000, but they got the 240. So if he passes, that means we're down to 249,760. Okay, that's basically the difference between the policy premium and how much they had to pay out. Now, the probability of these things, well, I do have the probability that he passes is 1 out of that very, very, very large number. Okay, but then so the probability he survives is all the rest of them. That's a lot of nines. Over. Okay. And so now to find our expected value, what we do is we take those values. So that 240 times that ugly looking fraction. Oops, I forgot some zeros up here. And then we're going to add the other piece, that negative 249,760, and the 1 over. Okay, and if I do this turns out to be 239.99975. If I did that correctly. Looking at what I had done previously, so I can just write the answer down. Okay, some things to kind of keep in mind, because our values of X are 240 and this is our lowest value, our average cannot exceed, can't get bigger than the largest positive, and it can't get smaller than the largest negative. So we're going to have somewhere between those two pieces. The chance of him passing is so small. That's why this big, huge negative does not impact the overall amount very much. So just kind of keep those things in mind as you're doing some of these problems and working through them. So for example, the first example that we did when Tommy was making baskets, our average has to be somewhere between 0 and 3. It is impossible for us to have an average of 4 baskets when he's only shooting 3, or a negative 2. In our second problem, when we were rolling the die and we were trying to figure out how much we could win or lose per game, well, we were only betting $4. The most we could win was $2. The most we would lose is all 4 of our dollars. And actually, we didn't even lose all 4 of our dollars because we always get at least $1 back. So the average per game won loss is somewhere between losing 3 and winning 2. It's not a huge win-loss situation. So kind of remember those rules of averages that still work. Your average is always going to have to be somewhere between the lowest and the highest value. And it will sway towards one or the other based on those probabilities. I hope this helps with your homework and other situations, your understanding for finding the average or expected value of a discrete probability distribution. See you in the next video.